Hello, how we doing? I thought I'd continue this audiobook, although I don't know if we'll get to the end of it by the end of today, because I have about an hour before I have to go to bed, and there's more than an hour's worth here, so. But we'll see. Give me a sec to set all this up. You can hear me typing on my keyboard. Sorry. Alright. Let me just share this out to people. Yeah, I'm curious. What screen is this going to land on? Alright, cool. Landed on the right one. Where do we go? Content sharing. Boom. It's the right link. We go in this one. We go that. Let's edit. Go. Sorry, I'm new to this. New to sharing my content because I figure I might as well, you know. Part 2. Alright, that's all I need to share with. And we'll see how we go from there. Now, where is this going to open up? It opens up over here. Alright, let's drag that there. We do that. We do that. I think we're good to go. Alright, let's do it. Part 2. So there's 12 or 13 chapters in this audiobook. It says 12, but there might be a hidden one. I don't know. So, and we are currently at 1 hour 26 minutes in, and it goes for 3 hours 41. So we have like 2 hours left. So yeah, there'll definitely be a part 3 in this. But yeah, let's get to it. Shout out again for Nature Relaxation Films for this footage, because it's freaking amazing. And it's not muted, but now it is, and we'll continue going.
Dark matter's effects are real. We just don't know what it is. Dark matter seems not to interact through the strong nuclear force, so it cannot make nuclei. It hasn't been found to interact through the weak nuclear force. Something even elusive neutrinos do. It doesn't seem to interact with the electromagnetic force, so it doesn't make molecules and concentrate into dense balls of dark matter. Nor does it absorb or emit or reflect or scatter light. As we've known from the beginning, dark matter does indeed exert gravity, to which ordinary matter responds. But that's it. After all these years, we haven't discovered it doing anything else. For now, we must remain content to carry dark matter along as a strange, invisible...
Hang on, I think I'm a little bit too far ahead. Crap. Let me have a look at my first stream. So I put it up at the very end in the chat. And it was 127.10. Oh no, we're right on. Right on it. Alright, cool.
...friend, invoking it where and when the universe requires it of us.
Here we go.
Chapter 6.
Chapter
Dark
6,
energy.
baby.
As if you didn't have enough to worry about, The universe in recent decades was discovered to wield a mysterious pressure that issues forth from the vacuum of space, and that acts opposite cosmic gravity.
Sorry about my squeaky chair as well.
Not only that, this negative gravity will ultimately win the tug of war as it forces the cosmic expansion to accelerate exponentially into the future. For the most mind-warping ideas of 20th century physics, just blame Einstein. Albert Einstein hardly ever set foot in the laboratory. He didn't test phenomena or use elaborate equipment. He was a theorist who perfected the thought experiment, in which you engage nature through your imagination by inventing a situation or model and then working out the consequences of some physical principle. In Germany, before World War II, laboratory-based physics far outranked theoretical physics in the minds of most Aryan scientists.
So World War II went from... I know when it ended, which is 1945. It started in 39, I think. So this is going a fair while back. 80 years, nearly.
Experiment in which you would to accelerate exponentially into the future. For the most mind-warping ideas of 20th century physics, just blame Einstein. Albert Einstein hardly ever set foot in the laboratory. He didn't test phenomena or use elaborate equipment. He was a theorist who perfected the thought experiment, in which you engage nature through your imagination by inventing a situation or model and then working out the consequences of some physical principle. In Germany, before World War II, laboratory-based physics far outranked theoretical physics in the minds of most Aryan scientists. Jewish physicists were all relegated to the lowly theorist's sandbox and left to fend for themselves. And what a sandbox that would become.
Yeah.
As was the case for Einstein, if a physicist model intends to represent the entire universe, then manipulating the model should be tantamount to manipulating the universe itself. Observers and experimentalists can then go out and look for the phenomenon predicted by that model. If the model is flawed, or if the theorists make a mistake in their calculations, the observers will uncover a mismatch between the model's predictions and the way things happen in the real universe. That's the first cue for a theorist to return to the proverbial drawing board by either adjusting the old model or creating a new one. One of the most powerful and far-reaching theoretical models ever devised, already introduced in these pages, is Einstein's general theory of relativity. But you can call it GR after you get to know it better. Published in 1916, GR outlines the relevant mathematical details of how everything in the universe moves under the influence of gravity.
Yep.
Every few years, lab scientists devise ever more precise experiments to test the theory, only to further extend the envelope of the theory's accuracy. A modern example of this stunning knowledge of nature that Einstein has gifted us comes from 2016, when gravitational waves were discovered by a specially designed observatory tuned for just this purpose. These waves, predicted by Einstein, are ripples moving at the speed of light across the fabric of space-time and are generated by severe gravitational disturbances such as the collision of two black holes. And that's exactly what was observed. The gravitational waves of the first detection were generated by a collision of black holes in a galaxy 1.3 billion light-years away, and at a time when Earth was teeming with simple single-celled organisms. While the ripple moved through space in all directions, Earth would, after another 800 million years, evolve complex life, including flowers and dinosaurs and flying creatures, as well as a branch of vertebrates called mammals. Among the mammals, a sub-branch would evolve frontal lobes and complex thought to accompany them. We call those primates. A single branch of these primates would develop a genetic mutation that allowed speech, and that branch, Homo sapiens, would invent agriculture and civilization and philosophy and art and science, all in the last 10,000 years. Ultimately, one of its 20th century scientists would invent relativity out of his head and predict the existence of gravitational waves. A century later, technology capable of seeing these waves would finally catch up with the prediction, just days before that gravity wave, which had been traveling for 1.3 billion years, washed over Earth and was detected. Yes, Einstein was a badass.
Yeah, he was.
When first proposed, most scientific models are only half-baked, leaving wiggle room to adjust parameters for a better fit to the known universe. In the sun-based heliocentric universe, conceived by the 16th century mathematician Nicholas Copernicus, planets orbited in circles. The orbit the sun part was correct and a major advance in the Earth-based geocentric universe, but
it all revolved around the Earth at that point. And I'm pretty sure everyone agreed with it, and it was up to someone who said, well, no, it's actually the sun. I think this was in part 1 as well, where someone came out and said, well, no, we orbit the sun. And that's how, he got shut down for that potential discrepancy back in the day, but nowadays, we all know that's true.
The circle part turned out to be a bit off. All planets orbit the sun in flattened circles, called ellipses, and even that shape is just an approximation of a more complex trajectory. Copernicus's basic idea was correct, and that's what mattered most. It simply required some tweaking to make it more accurate.
I like how it's ellipses, and then we see eclipses, so, from the sun or the moon. So, they must derive from the same, I'm guessing, Latin language.
Yet, in the case of Einstein's relativity, the founding principles of the entire theory require that everything must happen exactly as predicted. Einstein had, in effect, built what looks on the outside like a house of cards, with only 2 or 3 simple postulates holding up the entire structure. Indeed, upon learning of a 1931 book entitled 100 Authors Against Einstein, he responded that if he were wrong, then only one would have been enough.
Yep.
Therein were sown the seeds of one of the most fascinating blunders in the history of science.
So
Einstein's new
seeds,
equations of gravity included a term he called the cosmological constant, which he represented by the capital Greek letter lambda.
That one too.
A mathematically permitted but optional term, the cosmological constant allowed him to represent a static universe. Back then, the idea that our universe would be doing anything at all other than simply existing was beyond anyone's imagination. So lambda's sole job was to oppose gravity within Einstein's model, keeping the universe in balance, resisting the natural tendency for gravity to pull the whole universe into one giant mass. Einstein invented a universe that neither expands nor contracts, consistent with everybody's expectations at the time. The Russian physicist Alexander Friedmann would subsequently show mathematically that Einstein's universe, though balanced, was in an unstable state, like a ball resting on the top of a hill, awaiting the slightest provocation to roll down in one direction or another, or like a pencil balanced on its sharpened point. Einstein's universe was precariously perched between a state of expansion and total collapse. Moreover, Einstein's theory was new, and just because you give something a name does not make it real. Einstein knew that lambda, as a negative gravity force of nature, had no known counterpart in the physical universe.
So I've heard of lambda, but I don't know what it is. I know Neil's explaining it now, but it's hard to wrap my head around.
Einstein's general theory of relativity radically departed from all previous thinking about gravitational attraction. Instead of settling for Sir Isaac Newton's view of gravity as spooky action at a distance, a conclusion that made Newton himself uncomfortable, GR regards gravity as the response of a mass to the local curvature of space and time, caused by some other mass or field of energy. In other words, concentrations of mass cause distortions, dimples really, in the fabric of space and time. These distortions guide the moving masses along straight-line geodesics, the shortest distance between 2 points on a surface, though they look to us like the curved trajectories we call orbits. The 20th century American theoretical physicist John Archibald Wheeler said it best, summing up Einstein's concept as, Matter tells space how to curve. Space tells matter how to move.
Oh,
At the
wow.
end of the day,
That's cool.
general relativity described two kinds of gravity. One is the familiar kind, like the attraction between Earth and a ball thrown into the air, or between the sun and the planets. It also predicted another variety, a mysterious anti-gravity pressure associated with the vacuum of space-time itself. Lambda preserved what Einstein and every other physicist of his day had strongly presumed to be true: the status quo of a static universe. An unstable static universe. To invoke an unstable condition as the natural state of a physical system violates scientific credo. You cannot assert that the entire universe is a special case that happens to be balanced forever and ever.
No.
Nothing ever seen, measured, or imagined has behaved this way in the history of science, which makes for powerful...
Well, that being said, no one actually knows if this has happened before or not, so... and we'll never know. It's just a thing to ponder about.
Precedent. 13 years later, in 1929, the American astrophysicist Edwin P. Hubble discovered that the universe is not static. He had found and assembled convincing evidence that the more distant a galaxy, the faster the galaxy recedes from the Milky Way. In other words, the universe is expanding. Now, embarrassed by the cosmological constant, which corresponded to no known force of nature, and by the lost opportunity to have predicted the expanding universe himself, Einstein discarded lambda entirely, calling it his life's greatest blunder.
So it's interesting that Einstein can say that the universe is expanding and stuff like that back in his day, but now we actually have proof of that because there's something called redshift, which is when planets move or solar systems move further away. They turn into more harder light. I think it's infrared, which is red, and that's why it gets the name redshift. But if it was shrinking, it would produce like a blue light instead, in like the ultraviolet or something like that. So that's how we can tell that the universe is still expanding, which is crazy. And he didn't even know that back in, I don't know, when was he born? 1900s, something like that. It's crazy.
By yanking lambda from the equation, he presumed its value to be zero, such as in this example. Assume A equals B plus C. If you learn later that A equals 10 and B equals 10, then A still equals B plus C, except in that case C equals 0, and it's rendered unnecessary in the equation. But that wasn't the end of the story. Off and on over the decades, theorists would extract lambda from the crypt, imagining what their ideas would look like in a universe that had a cosmological constant. 69 years later, in 1998, science exhumed lambda one last time. Early that year, remarkable announcements were made by two competing teams of astrophysicists, one led by Saul Perlmutter of Lawrence Berkeley National Laboratory in Berkeley, California, and the other co-led by Brian Schmidt of Mount Stromlo and Siding Spring Observatories in Canberra, Australia, and Adam Rees of the Johns Hopkins University in Baltimore, Maryland. Dozens of the most distant supernovas ever observed appeared noticeably dimmer than expected, given the well-documented behavior of this species of exploding star. Reconciliation required that either those distant supernovas behaved unlike their nearer brethren, or they were as much as 15% farther away than where the prevailing cosmological models had placed them. The only known thing that naturally accounts for this acceleration is Einstein's lambda, the cosmological constant. When astrophysicists dusted it off and put it back into Einstein's original equations for general relativity, the known state of the universe matched the state of Einstein's equations. Wow. The supernovas used in Perlmutter's and Schmidt's studies are worth their weight in fusionable nuclei. Within certain limits, each of those stars explodes the same way, igniting the same amount of fuel.
That's actually insane that, like, Einstein predicted these things and then we can come up with it many years later and say, yeah, no, he's correct. That's crazy, man.
Releasing the same titanic amount of energy in the same amount of time, thereby reaching the same peak luminosity. Thus, they serve as a kind of yardstick or standard candle for calculating cosmic distances to the galaxies in which they explode out to the farthest reaches of the universe. Standard candles simplify calculations immensely. Since the supernovas all have the same wattage, the dim ones are far away and the bright ones are close by. After measuring their brightness, a simple task, you can tell exactly how far they are from you and from one another. If the luminosities of the supernovas were all different, you could not use brightness alone to tell how far away one was in comparison with another. A dim one could be either a high wattage bulb far away or a low wattage bulb close up. All fine,
No,
but there's a second way to measure the distance to the galaxies, their speed of recession from the Milky Way.
Yeah.
Recession that's part and parcel of the overall cosmic expansion.
That's what I'm saying.
As Hubble was the first to show,
The light
the
changes.
expanding universe makes distant objects race away from us faster than nearby ones. So, by measuring a galaxy's speed of recession, another simple task, one can deduce a galaxy's distance. If those two well-tested methods give different distances for the same object, something must be wrong. Either the supernovas are bad standard candles, or a model for the rate of cosmic expansion as measured by galaxy speeds is wrong. Well, something was wrong. It turned out that the supernovas were splendid standard candles, surviving the careful scrutiny of many skeptical investigators. And so astrophysicists were left with a universe that had expanded faster than we thought, placing galaxies farther away than their recession speed would have otherwise indicated. And there was no easy way to explain the extra expansion without invoking lambda, Einstein's cosmological constant.
I don't know, lambda.
Here was the first direct evidence that a repulsive force permeated the universe, opposing gravity, which is how and why the cosmological constant rose from the dead. Lambda suddenly acquired a physical reality that needed a name, and so dark energy took center stage in the cosmic drama, suitably capturing both the mystery and our associated ignorance of its cause. Perlmutter, Schmidt, and Rees justifiably shared the 2011 Nobel Prize in Physics for this discovery. The most accurate measurements to date reveal dark energy as the most prominent thing in town, currently responsible for 68% of all the mass energy in the universe. Dark matter comprises 27%, with regular matter comprising a mere 5%. The shape of our four-dimensional universe comes from the relationship between the amount of matter and energy that lives in the cosmos and the rate at which the cosmos is expanding. A convenient mathematical measure of this is omega, yet another capital Greek letter with a firm grip on the cosmos. If you take the matter-energy density of the universe and divide it by the matter-energy density required to just barely halt the expansion, known as the critical density, you get omega. Since both mass and energy cause space-time to warp or curve, omega tells us the shape of the cosmos. If omega is less than 1, the actual mass energy falls below the critical value, and the universe expands forever in every direction for all of time, taking on the shape of a saddle in which initially parallel lines diverge. If omega equals 1, the universe expands forever, but only barely so. In that case, the shape is flat, preserving all the geometric rules we learned in high school about parallel lines. If omega exceeds 1, parallel lines converge, and the universe curves back on itself, ultimately recollapsing into the fireball whence it came. At no time since Hubble discovered the expanding universe has any team of observers ever reliably measured omega to be anywhere close to 1. Adding up all the mass and energy their telescopes could see, and even extrapolating beyond these limits, dark matter included, the biggest values from the best observations topped out at about omega equals 0.3.
Oh, wow.
As far as observers were concerned, the universe was open for business, riding a one-way saddle into the future. Meanwhile, beginning in 1979, the American physicist Alan H. Guth of the Massachusetts Institute of Technology and others advanced an adjustment to the Big Bang theory that cleared up some nagging problems with getting a universe to be as smoothly filled with matter and energy as ours is known to be. A fundamental byproduct of this update to the Big Bang was that it drives omega toward 1, not toward a half, not toward 2, not toward a million, toward 1. Hardly a theorist in the world had a problem with that requirement, because it helped get the Big Bang to account for the global properties of the known universe. There was, however, another little problem. The update predicted 3 times as much mass energy as observers could find. Undeterred, the theorists said the observers just weren't looking hard enough. At the end of the tallies, visible matter alone could account for no more than 5% of the critical density. How about the mysterious dark matter? They added that too. Nobody knew what it was, and we still don't know what it is, but surely it contributed to the totals. From there, we get 5 or 6 times as much dark matter as visible matter. But that's still way too little. Observers were at a loss, and the theorists answered, keep looking. Both camps were sure the other was wrong, until the discovery of dark energy. That single component, when added to the ordinary matter and the ordinary energy and dark matter, raised the mass energy density of the universe to the critical level, simultaneously satisfying both the observers.
So what's the critical level? I don't know what that is. Is that like critical level as in temperature or reference points, like what people know, or... I'm not too sure. Never heard of this before.
And the theorists. For the first time, the theorists and observers kissed and made up. Both, in their own way, were correct. Omega does equal 1, just as the theorists demanded of the universe, even though you can't get there by adding up all the matter, dark or otherwise, as they had naively presumed. There's no more matter running around the cosmos today than had ever been estimated by the observers. Nobody had foreseen the dominating presence of cosmic dark energy, nor had anybody imagined it as the great reconciler of differences. So what is the stuff? Nobody knows. The closest anybody has come is to presume dark energy is a quantum effect, where the vacuum of space, instead of being empty, actually seethes with particles and their antimatter counterparts. They pop in and out of existence in pairs and don't last long enough to be measured. Their transient existence is captured in their moniker, virtual particles. The remarkable legacy of quantum physics, the science of the small, demands that we give this idea serious attention. Each pair of virtual particles exerts a little bit of outward pressure as it ever so briefly elbows its way into space.
So yeah, I like how we've known about quantum mechanics for so long, and dark matter, and all sorts of other things that we can't detect. We know they're there, but we just can't detect them. So that obviously is a flaw with our science, or something to do with that. Like, if we were really good at science and could work out everything, then we'd know what it was, but obviously we can't detect it yet. Obviously it might take a couple 100 years, or maybe even 10 years, who knows? And we might find out what dark matter is. I reckon it's like an opposite end of the elements that we have, like that what we know, and we just have no way of detecting the opposite end of those elements. You know what I mean?
Unfortunately, when you estimate the amount of repulsive vacuum pressure that rises from the abbreviated lives of virtual particles, the result is more than 10 to the power 120 times larger than the experimentally determined value of the cosmological constant. This is a stupidly large factor, leading to the biggest mismatch between theory and observation in the history of science. Yes, we're clueless, but it's not abject cluelessness. Dark energy is not adrift with nary a theory to anchor it. Dark energy inhabits one of the safest harbors we can imagine, Einstein's equations of general relativity. It's the cosmological constant. It's lambda. Whatever dark energy turns out to be, we already know how to measure it and how to calculate its effects on the past, present, and future of the cosmos. Without a doubt, Einstein's greatest blunder was having declared that lambda was his greatest blunder.
Yeah, I still don't know what.
And the hunt is on. Now that we know dark energy is real, teams of astrophysicists have begun ambitious programs to measure distances and the growth of structure in the universe using ground-based and spaceborne telescopes. These observations will test the detailed influence of dark energy on the expansion history of the universe, and will surely keep theorists busy. They desperately need to atone for how embarrassing their calculation of dark energy turned out to be. Do we need an alternative to GR? Does the marriage of GR and quantum mechanics require an overhaul? Or is there some theory of dark energy that awaits discovery by a clever person yet to be born? A remarkable feature of lambda and the accelerating universe is that the repulsive force arises from within the vacuum, not from anything material. As the vacuum grows, the density of matter and familiar energy within the universe diminishes, and the greater becomes lambda's relative influence on the cosmic state of affairs. With greater repulsive pressure comes more vacuum, and with more vacuum comes greater repulsive pressure, forcing an endless and exponential acceleration of the cosmic expansion. As a consequence, anything not gravitationally bound to the neighborhood of the Milky Way galaxy will recede at ever-increasing speed as part of the accelerating expansion of the fabric of space-time.
That's what I was saying.
Distant galaxies, now visible in the night sky, will ultimately disappear beyond an unreachable horizon, receding from us faster than the speed of light. A feat allowed not because they're moving through space at such speeds, but because the fabric of the universe itself carries them at such speeds. No law of physics prevents this. In 1 trillion or so years, anyone alive in our own galaxy may know nothing of other galaxies. Our observable universe will merely comprise a system of nearby long-lived stars within the Milky Way, and beyond this starry night will lie an endless void. Darkness in the face of the deep. Dark energy, a fundamental property of the cosmos, will, in the end, undermine the ability of future generations to comprehend the universe they've been dealt. Unless contemporary astrophysicists across the galaxy keep remarkable records and bury an awesome trillion-year time capsule, post-apocalyptic scientists will know nothing of galaxies, the principal form of organization for matter in our cosmos, and will thus be denied access to key pages from the cosmic drama that is our universe. Behold my recurring nightmare. Are we, too, missing some basic pieces of the universe that once were? What part of the cosmic history book has been marked access denied? What remains absent from our theories and equations that ought to be there, leaving us groping for answers?
That's what I'm saying. We don't know what dark matter is, but I bet you we'll find it in, I don't know,
Chapter 7.
a couple years.
The Cosmos on the Table.
Oh, Chapter 7.
Trivial questions sometimes require deep and expansive knowledge of the cosmos just to answer them. In middle school chemistry class, I asked my teacher where the elements on the periodic table came from. He replied, Earth's crust. I'll grant him that. It's surely where the supply lab gets them, but how did Earth's crust acquire them? The answer must be astronomical.
Space.
But in this case, do you actually need to know the origin and evolution of the universe to answer the question? Yes, you do. Only 3 of the naturally occurring elements were manufactured in the Big Bang. The rest were forged in the high-temperature hearts and explosive remains of dying stars, enabling subsequent generations of star systems to incorporate this enrichment, forming planets, and in our case, people.
It really is, Yoon. It's
For many,
crazy.
the periodic table of chemical elements is a forgotten oddity, a chart of boxes filled with mysterious cryptic letters lasting...
It's just too hard to comprehend. This book is called Astrophysics for people in a hurry. This is not in a hurry. You have to think about stuff.
countered on the wall of high school chemistry class. As the organizing principle for the chemical behavior of all known and yet to be discovered elements in the universe, the table instead ought to be a cultural icon, a testimony to the enterprise of science as an international human adventure conducted in laboratories, particle accelerators, and on the frontier of the cosmos itself. Yet, every now and then, even a scientist can't help thinking of the periodic table as a zoo of one-of-a-kind animals conceived by Dr. Seuss. How else could we believe that sodium is a poisonous reactive metal that you can cut with a butter knife, while pure chlorine is a smelly, deadly gas, yet when added together, they make sodium chloride, a harmless, biologically essential compound better known as table salt? Or how about hydrogen and oxygen? One is an explosive gas and the other promotes violent combustion, yet the two combined make liquid water, which puts out fires. Amid these chemical confabulations, we find elements significant to the cosmos, allowing me to offer the periodic table as viewed through the lens of an astrophysicist.
I've never thought of that. That's crazy. What?
With only one proton in its nucleus, hydrogen is the lightest and simplest element, made entirely during the Big Bang. Out of the 94 naturally occurring elements, hydrogen lays claim to more than 2/3 of all the atoms in the human body, and more than 90% of all atoms in the cosmos, on all scales, right on down to the solar system. Hydrogen in the core of the massive planet Jupiter is under so much pressure that it behaves more like a conductive metal than a gas, creating the strongest magnetic field among the planets. The English chemist Henry Cavendish discovered hydrogen in 1766 during his experiments with H2O. Hydrogenesis is Greek for water forming, but he's best known among astrophysicists as the first to calculate Earth's mass after having measured an accurate value for big G, the gravitational constant in Newton's famous equation.
I can't move off the fact that he said hydrogen was a flammable thing, which is known, and oxygen fuels a fire, but when they're combined, it creates water, which puts out fires. I never thought of it that way. That's crazy.
Every second of every day, 4.5 billion tons of fast-moving hydrogen nuclei are turned into energy as they slam together to make helium within the 15 million degree core of the sun. Helium is widely recognized as an over-the-counter low-density gas that, when inhaled, temporarily increases the vibrational frequency of your windpipe and larynx, making you sound like Mickey Mouse. Helium is the second simplest and second most abundant element in the universe. Although a distant second to hydrogen
is
in abundance,
first. Yep.
There's 50 times more of it than all other elements in the universe combined.
Holy shit.
One of the pillars of Big Bang cosmology is the prediction that in every region of the cosmos, no less than about 10% of all atoms are helium.
So wait, helium's more abundant than hydrogen? I mean, I was going to say that doesn't make sense because the periodic table goes hydrogen, helium, lithium. But I guess it goes off the atomic mass for the periodic table. So hydrogen is still first. But yeah, I never knew that because like on planet Earth, we're trying to harvest helium and all that sort of stuff, and we're apparently running out, from what I've heard through multiple things, but I don't know if that's true or not. We'll probably find more, but yeah. Can we find helium in mine deposits? Like we do with helium? I don't know.
Manufactured in that percentage across the well-mixed primeval fireball that was the birth of our universe. Since the thermonuclear fusion of hydrogen within stars gives you helium, some regions of the cosmos could easily accumulate more than their 10% share of the stuff, but as predicted, no one has ever found a region of the galaxy with less. Some 30 years before it was discovered and isolated on Earth, astronomers detected helium in the spectrum of the sun's corona during the total eclipse of 1868. As noted earlier, the name helium was duly derived from Helios, the Greek sun god, and with 92% of hydrogen's buoyancy in air, but without its explosive characteristics, helium is the gas of choice for the outsized balloon characters of the Macy's Thanksgiving Day Parade, making the department store second only to the U.S. military as the nation's top user of the element.
I don't know what that is. Any of you guys know what the Macy's Parade is? Because I have no idea. I guess it's like a whole bunch of helium balloons and stuff walking through a street. That'd be my guess.
Is the third simplest element in the universe, with 3 protons in its nucleus. Like hydrogen and helium, lithium was made in the Big Bang. But unlike helium, which can be manufactured in stellar cores, lithium is destroyed by every known nuclear reaction. Another prediction of Big Bang cosmology is that we can expect no more than 1% of the atoms in any region of the universe to be lithium.
That's crazy, because most batteries are made out of the lithium ion, currently. And it's 1% in the solar system, or universe, sorry. I mean, that means, like, there's so much stuff out there, but still, I can't believe we have so much lithium on our planet to be able to do that, to make batteries out of.
No one has yet found a galaxy with more lithium than this upper limit supplied by the Big Bang. The combination of helium's upper limit and lithium's lower limit gives us a potent dual constraint on tests for Big Bang cosmology. The element carbon can be found in more kinds of molecules than the sum of all other kinds of molecules combined. Given the abundance of carbon in the cosmos, forged in the cores of stars, churned up to their surfaces, and released copiously into the galaxy, a better element does not exist on which to base the chemistry and diversity of life.
Silicon might
Just
be
edging
second.
out carbon in abundance rank, oxygen is common too, forged and released in the remains of exploded stars. Both oxygen and carbon are major ingredients of life as we know it. But what about life as we don't know it? How about life based on the element silicon? Silicon sits directly below carbon on the periodic table, which
what I was
means
saying,
in principle,
boy.
it can create the same portfolio of molecules that carbon does. In the end, we expect carbon to win because it's 10 times more abundant than silicon in the cosmos, but that doesn't stop science fiction writers who keep exobiologists on their toes, wondering what the first truly alien silicon-based life forms would be like. In addition to being an active ingredient in table salt, sodium is the most common glowing gas in municipal street lamps across the nation. They burn brighter and longer than incandescent bulbs, although they may all soon be replaced by LEDs, which are even brighter at a given wattage and cheaper. 2 varieties of sodium lamps are common: high-pressure lamps, which look yellow-white, and the rarer low-pressure lamps, which look orange. Turns out, while all light pollution is bad for astrophysics, the low-pressure sodium lamps are least bad because their contamination can be easily subtracted from telescope data. In a model of cooperation, the entire city of Tucson, Arizona, the nearest large municipality to the Kitt Peak National Observatory, has, by agreement with the local astrophysicists, converted all its streetlights to low-pressure sodium lamps.
Well, that's
Aluminum
nice of them.
occupies nearly 10% of Earth's crust, yet was unknown to the ancients and unfamiliar to our great-grandparents. The element was not isolated and identified until 1827 and did not enter common household use until the late 1960s, when tin cans and tinfoil yielded to aluminum cans and, of course, aluminum foil. I'd bet...
Yeah, don't mind the old aluminium cans. Or aluminum cans. That's what I'm drinking my beers out of now. Good old aluminium.
Most old people you know still call it tin foil. Polished aluminum makes a near-perfect reflector of visible light and is the coating of choice for nearly all telescope mirrors today. Titanium is 1.7 times denser than aluminum, but it's more than twice as strong, So titanium, the ninth most abundant element in Earth's crust, has become a modern darling for many applications, such as military aircraft components and prosthetics that require a light, strong metal for their tasks. In most cosmic places, the number of oxygen atoms exceeds that of carbon. After every carbon atom has latched onto the available oxygen atoms, forming carbon monoxide or carbon dioxide, the leftover oxygen bonds with other things like titanium. The spectra of red stars are riddled with features traceable to titanium oxide, which itself is no stranger to stars on Earth. Star sapphires and rubies owe their radiant asterisms to titanium oxide impurities in their crystal lattice. Furthermore, the white paint used for telescope domes features titanium oxide, which happens to be highly reflective in the infrared part of the spectrum, greatly reducing the heat accumulated from sunlight in the air surrounding the telescope. At nightfall, with the dome open, the air temperature near the telescope rapidly equals the temperature of the nighttime air, allowing light from stars and other cosmic objects to be sharp and clear. And, while not directly named for a cosmic object, titanium derives from the Titans of Greek mythology. Titan is Saturn's largest moon. By many measures, iron ranks as the most important element in the universe. Massive stars manufacture elements in their core, in sequence from helium to carbon to oxygen to nitrogen and so forth, all the way up the periodic table to iron. With 26 protons and at least as many neutrons in its nucleus, iron's odd distinction comes from having the least total energy per nuclear particle of any element. This means something quite simple. If you split iron atoms via fission, they will absorb energy. And if you combine iron atoms via fusion, they will also absorb energy. Stars, however, are in the business of making energy. As high-mass stars manufacture and accumulate iron in their cores, they are nearing death. Without a fertile source of energy, the star...
Yeah, so I think the last life of a star is when they start burning the heavier elements into iron. And once that starts to happen, it goes down pretty quick, from what I've heard. Or from what I've read. Well, and heard on YouTube videos.
Star collapses under its own weight and instantly rebounds in a stupendous supernova explosion, outshining 1 billion suns for more than a week.
Oh, wow. A week.
The soft metal gallium has such a low melting point that, like cocoa butter, it will liquefy on contact with your hand.
Yeah, so have you guys ever used gallium? Like, you can put it in your hand and it's a solid before it goes in your hand, but then the temperature of, like, the temperature of your palm makes it go to liquid. It's pretty interesting.
Apart from this parlor demo, gallium is not interesting to astrophysicists except as one of the ingredients in the gallium chloride experiments used to detect elusive neutrinos from the sun. A 100-ton underground vat of liquid gallium chloride is monitored for any collisions between neutrinos and gallium nuclei. For every successful slam, gallium temporarily becomes germanium. The germanium eventually decays back.
I think germanium is right after arsenic, if I remember my periodic table correctly. I don't know the number of that, but I just know, like, the first 40 elements in a row, so...
into gallium, emitting a detectable pulse of X-rays. The long-standing problem, where fewer solar neutrinos were detected than predicted by solar theory, was solved using telescopes such as this. Every form of the element technetium is radioactive.
Oh no.
Not surprisingly,
sorry, it
it's
goes
found nowhere
germanium
on Earth
before
except
arsenic.
in nuclear reactors and particle accelerators, where we make it on demand. Technetium carries this distinction in its name, which derives from the Greek teknetos, meaning artificial. For reasons not fully understood, technetium lives in the atmospheres of a select subset of red stars. This alone would not be cause for alarm, except that long-lived technetium has a half-life of just a few million years, which is much, much shorter than the age and life expectancy of the stars in which it is found. In other words, the star cannot have been born with the stuff, for if it were, there would be none left by now. There is also no known mechanism to create technetium in a star's core and have it dredge itself up to the surface where it is observed, which has led to exotic theories that have yet to achieve consensus in the astrophysics community. Along with osmium and platinum, iridium is one of the 3 heaviest, densest elements on the table. 2 cubic feet of it weighs as much as a Buick, which makes iridium one of the world's best paperweights, able to defy all known office fans. Iridium is also the world's most famous smoking gun. A thin layer of it can be found worldwide at the famous Cretaceous-Paleogene boundary, formerly known as the KT boundary in geologic strata, dating from 65 million years ago. Not so coincidentally, that's when every land species larger than a carry-on suitcase went extinct, including the legendary dinosaurs. Iridium is rare on Earth's surface, but relatively common in 6-mile metallic asteroids, which, upon colliding with Earth, vaporized on impact, scattering their atoms across Earth's surface. So, whatever might have been your favorite theory for offing the dinosaurs, a killer asteroid the size of Mount Everest from outer space should be at the top of your list. I don't know how Albert would have felt about this, but an unknown element was discovered in the debris of the first hydrogen bomb test in the Eniwetok Atoll in the South Pacific on November 1st, 1952, and was named Einsteinium in his honor.
Oh, well.
I might have named it Armageddonium instead. Meanwhile, 10 entries in the periodic table get their names from objects that orbit the sun. Phosphorus comes from the Greek for light-bearing, and was the ancient name for the planet Venus when it appeared before sunrise in the dawn sky. Selenium comes from Selene, which is Greek for the moon, named so because in ores it was always associated with the element tellurium, which had already been named for Earth, from the Latin tellus. On January 1st, 1801, the Italian astronomer Giuseppe Piazzi discovered a new planet orbiting the Sun in the suspiciously large gap between Mars and Jupiter. Keeping with the tradition of naming planets after Roman gods, the object was named Ceres, after the goddess of agriculture and grains. Ceres is, of course, the root of the word cereal. At the time, there was sufficient excitement in the scientific community for the first element discovered after this date to be named Cerium in its honor. 2 years later, another planet was discovered orbiting the Sun in the same gap as Ceres.
No.
This one was named Pallas, after the goddess of wisdom, Pallas Athena. And, like Cerium before it, the first element discovered thereafter was named Palladium in its honor. The naming party would end a few decades later, after dozens more of these planets were discovered sharing the same orbital zone. Closer analysis revealed that these objects were much, much smaller than the smallest known planets. A new swath of real estate had been discovered in the solar system, populated by small, craggy chunks of rock and metal. Ceres and Pallas were not planets. They are asteroids, and they live in the asteroid belt, now known to contain hundreds of thousands of objects, somewhat more than the number of elements in the periodic table. The metal Mercury, liquid and runny at room temperature, and the planet Mercury, the fastest of all planets in the solar system, are both named for the speedy Roman messenger god of the same name. Thorium is named for Thor, the hunky lightning bolt-wielding Scandinavian god who corresponds with lightning bolt-wielding Jupiter in Roman mythology. And, by Jove, Hubble Space Telescope images of Jupiter's polar regions reveal extensive electrical discharges deep within its turbulent cloud layers.
A shout out to Chris Hemsworth, who plays Thor in the Avatar movies. Also Australian.
Alas, Saturn, my favorite planet, has no element named for it, But Uranus, Neptune, and Pluto are famously represented.
Uranium,
the element
Neptunium,
uranium
and
was
plutonium.
discovered in 1789 and named in honor of the planet discovered by William Herschel just 8 years earlier. All isotopes of uranium are unstable, spontaneously decaying to lighter elements, a process accompanied by the release of energy. The first atomic bomb ever used in warfare had uranium as its active ingredient and was dropped by the United States, incinerating the Japanese city of Hiroshima on August 6, 1945. With 92 protons packed in its nucleus, uranium is widely described as the largest naturally occurring element, although trace amounts of larger elements can be found naturally where uranium ore is mined. If Uranus deserved an element named in its honor, then so did Neptune. Unlike uranium, however, which was discovered shortly after the planet, Neptunium was discovered in 1940 in the Berkeley cyclotron, a full 94 years after the German astronomer Johann Galle found Neptune in a spot on the sky predicted by the French mathematician Urbain Le Verrier after studying Uranus's odd orbital behavior. Just as Neptune comes right after Uranus in the solar system, so too does Neptunium come right after uranium in the periodic table of elements.
Mm-hmm.
The Berkeley cyclotron discovered or manufactured many elements not found in nature, including plutonium, which directly follows Neptunium in the table and was named for Pluto, which Clyde Tombaugh discovered at Arizona's Lowell Observatory in 1930. Just as with the discovery of Ceres 129 years earlier, excitement prevailed. Pluto was the first planet discovered by an American and, in the absence of better data, was widely regarded as an object of commensurate size and mass to Earth, if not Uranus or Neptune. As our attempts to measure Pluto's size became more and more refined, Pluto kept getting smaller and smaller. Our knowledge of Pluto's dimensions did not stabilize until the late 1980s. We now know that cold, icy Pluto is by far the smallest of the 9, with the diminutive distinction of being littler than the solar system's 6 largest moons. And like the asteroids, hundreds more objects were later discovered in the outer solar system, with orbits similar to that of Pluto.
See, that's interesting. I thought Pluto was on the same mass as Mercury, but I guess not. It's wild.
Signaling the end of Pluto's tenure as a planet, and the revelation of a heretofore undocumented reservoir of small icy bodies called the Kuiper Belt of comets, to which Pluto belongs. In this regard, one could argue that Ceres, Pallas, and Pluto slipped into the periodic table under false pretenses. Unstable, weapons-grade plutonium was the active ingredient in the atomic bomb that the United States exploded over the Japanese city of Nagasaki just 3 days after Hiroshima.
Okay, so they had 2 different types of bombs, and one was plutonium and one was uranium-based. I did not know that. Why not make 2 of the same bombs? Why do 1 plutonium and 1 uranium?
Bringing a swift end to World War II, small quantities of non-weapons-grade radioactive plutonium can be used to power radioisotope thermoelectric generators, sensibly abbreviated as RTGs, for spacecraft that travel to the outer solar system, where the intensity of sunlight has diminished below the level usable by solar panels. 1 pound of plutonium will generate 500,000 kilowatt-hours of heat energy, enough to continuously power a household blender for 100 years, or a human being for 5 times as long, if we ran on nuclear fuel instead of grocery store food. So ends our cosmic journey through the periodic table of elements, right to the edge of the solar system and beyond. For reasons I've yet to understand, many people don't like chemicals, which might explain the perennial movement to rid foods of them. Perhaps sesquipedalian chemical names just sound dangerous. But in that case, we should blame the chemists and not the chemicals themselves. Personally, I'm quite comfortable with chemicals anywhere in the universe. My favorite stars, as well as my best friends, are all made of them.
That's it.
Chapter 8.
Alright, we're ending it here. Thank you so much for tuning in. It's a short stream, but we currently have 1 hour and 30 minutes to do. Sorry, in I don't know when, but I'm going to post this here just so I don't forget where we're up to. And I hope you guys enjoyed. I have a couple friends online, so I might stream something else, but for the time being, be sure to sub and no, just subscribe. That's all I want. I don't want likes or anything. Just sub and you'll get notified of when I'm doing part 3, which might be the finale, which will be in, I don't know, my days off Tuesday, Wednesday, and today is Saturday, so a couple days, I guess. And we'll see how we go from there. But I hope you guys enjoyed, and I will catch you all very soon to do part 3, the finale. I prefer to do that on my days off, where I don't have to worry about going to bed to go to work and all that sort of stuff. So we have an hour and a half to go. Alright. Catches.